Hello everyone. In this video, I would like to take a look at the concavity of a function. Basically, concavity tells us when a function bends upwards or it bends downwards. So specifically, what I would like to take a look is how we figure out where a function is concave up or where the function is concave down. To do that, we're going to use the test for concavity. So let's take a look at that right away. It says let f be a function that is continuous on a closed interval from a to b. And we also need the first derivative and the second derivative to exist on this interval. The test for concavity, if the second derivative of x is greater than 0 on the interval, then the function is concave up. And if the second derivative is negative, if it's less than 0 on that interval from a to b, then our function is concave down. So the first thing, let's figure out why the second derivative tells us the concavity of a function. So I'm just going to take a look at two simple, specific examples. So the first one, let's think about the positive portion of the x squared function. So we'll say that this is y is equal to x squared. And then let's also take a look at our square root function that looks something like this. Now both of these are increasing functions, meaning as we go from left to right, our y values are getting bigger, and also the slopes of the tangent lines are all positive. Furthermore, both of these functions also pass through the point 1, 1. So they have a lot in common, but the relative shapes, as you can see, are very different. One of these is concave up, and one of them is concave down. So if I draw in some of our tangent lines, so for my x squared function, if you can imagine these tangent lines, as I move from left to right, these tangent lines are getting steeper and steeper. So that means that the rate of change of the first derivative, since the first derivative tells us the slopes of the tangent lines, the rate of change of that first derivative is increasing. In other words, the second derivative is positive. So as I move from left to right, because the slopes of my tangent lines are increasing, they're getting steeper, the second derivative has to be positive. If I take a look at the tangent lines on my square root function, as I move from left to right, these are getting less steep. They're flattening out. So the slopes of my tangent lines are decreasing. They're approaching 0, I could say, which means that the second derivative, which is the rate of change of the first derivative, the second derivative has to be negative. They're decreasing. Another thing I can take a look at here is the location of these tangent lines, and that can help me determine if it's concave up or concave down. So for my x squared function, all of the tangent lines are below the graph of my function. But for the square root function, all these tangent lines are above my function. So when all the tangent lines are below, this is going to be concave up. And when all the tangent lines are above, this is concave down. And so in general, taking a look at their overall shapes, if my function is bending upwards, I say it's concave up. And if it's bending down, it's going to be concave down. All right, so now let's use the test in a specific example. So I have a function f of x is equal to x cubed minus 6x squared plus 9x plus 30. And I want to do a couple things here. I want to take a look at the local extrema for this function, and then I want to determine where this is concave up and where it's concave down. So the first thing, to find the local extrema, we can use the first derivative test. So the first derivative test, we need to find the critical numbers, and then we're going to test the intervals to see if my function is increasing or decreasing on either side of the critical numbers. So the first step, let's find our first derivative. So the power rule, we get 3x squared minus 12x plus 9. And now our critical numbers are going to occur whenever this is equal to 0 or it's undefined. But this is just a polynomial, so I don't need to worry about the undefined ones. So I'm just going to factor this as much as I can. I can factor out a 3, and that leaves me with x squared minus 4x plus 3. And now factoring that trinomial, we're going to end up with x minus 1 and x minus 3. So taking a look at that, we can see our critical numbers are going to occur at x is equal to 1 and at x is equal to 3. So now I'm going to use a sign chart to help me determine where this function is increasing and where it's decreasing. So these two critical numbers, they take our interval, they take our domain, and they split it up into 3 intervals. So we have the first interval that goes from -infinity all the way up to +1. We have the interval for everything in between 1 and 3, and we have the interval from 3 to +infinity. And now we just want to test each one of these to see whether our derivative, our first derivative, is positive or negative, and that will tell us if our function is increasing or decreasing. So if I pick out a number that's less than 1, so for example, 0, this first set of parentheses would be negative, the second one would also be negative, so a negative number times a negative number, I get a positive. In the middle, so if I pick out a number that's in between 1 and 3, for example, I could pick out 2, but I am just concerned with the overall sign. So this one would end up being positive because it's a number bigger than 1. But the second set of parentheses would be negative because the number is still smaller than 3. So we have a positive number times a negative number, so we get a negative. And then lastly, if I pick out a number bigger than 3, we'll have a positive times a positive. So that means our function's increasing on this interval. So when my function goes from increasing to decreasing, this is going to be a local max. And when I go from decreasing to increasing, here we're going to have a local minimum. And why don't we just evaluate these so we can specifically see what the points are going to be for our maximum and minimum. So we need to know f of 1, and we also need to know f of 3. So let's see what we get. So for f of 1, we have 1 cubed minus 6 times 1 plus 9 times 1 plus 30. So overall, that's going to be -5 plus 9 is 4. So 4 plus 30, we get 34. And for f of 3, let's see, 3 cubed is 27. And then minus 6 times 3 squared. So 3 squared is 9. 6 times 9, we get minus 54. Plus 9 times 3, which is 27, plus 30. So overall, 27 minus 54 plus 27, that's actually going to be 0. So we just end up with 30. So we have a max, a local max, at the point 1, 34. And we have a local minimum at the point 3 and 30. So there's our two extrema. And now the second thing I wanted to do on this was I wanted to find out where this function is concave up and where it's concave down. To do that, we're going to use this second derivative. So let's find f double prime. So f double prime, we're going to take the derivative of our first derivative. So again, power rule. Let's see, we end up with 3 times 2, we get 6x minus 12. And now if we just kind of take a look at where this is going to be equal to 0. So if I set that equal to 0, and I factor, we get 6 times x minus 2. So that means that at x is equal to 2, our second derivative is 0. So that point, that's going to take our domain and split it up into two parts. So that's what's going to decide our intervals that we want to test for concavity. So we want to test all the numbers that are less than 2, and we want to test all the numbers that are bigger than 2. So if we pick out something smaller than 2, so for example, again, we could pick out 0. So here we'll end up with something that's negative times 6, so we have a negative here. So our second derivative is less than 0, which means that this interval is going to be concave down. And now if I pick out something bigger than 2, I'll end up with a positive times 6. I also get a positive. So what that means is my function is concave down on that first interval from negative infinity to 2. And my function is concave up on that second interval from 2 to infinity. Now, the reason I wanted to do this, and I wanted to compare our first derivative, our local extrema, and I wanted to take a look at the concave up and down, is because I wanted to point out that they're not necessarily the same. So where our function changes from increasing to decreasing, or decreasing to increasing, that indicates a local maximum or a local minimum. That doesn't indicate where the function is concave up or concave down. So that's why we need to take a look at the second derivative, because now we only have 2 intervals to consider. Half of our domain is concave down, the other half is concave up. So why don't we just finish up by taking a look at the graph of this function, just so we can verify all these, what we saw here. So if I type in my function, so I have x cubed and minus 6x squared and plus 9x plus 30. And then let's adjust our window right away so we can make sure we get everything in here. So we have a maximum and a minimum at 1 and 3. So we need to make sure we get those x values in there. So I'm actually just going to go from 0, and then a little bit to the right of 3 will go up to 5. And now the y values for our maximum and minimum, we have 30 and 34. So this is pretty high in the y direction. So why don't we go from 25, and then we need to include 34, so I'm going to go up to 40. And then let's take a look at our graph here. Okay, so we do need to remember that this does continue on forever. This will approach negative infinity as I go towards negative infinity. But as I can see, so at 1, I have a local maximum. At 3, I have a local minimum. But that doesn't necessarily mean my function changes from concave up to concave down at these points. My function actually changes concavity at x is equal to 2. So as we can see, my function is bending downwards until I get to 2. And then here it switches and now it's bending upwards. If we think about the tangent lines, all the tangent lines are above my function until I get to 2. And then at 2, now all the tangent lines are going to be below. And that also indicates that my function is concave down from negative infinity up to 2, and then concave up from 2 to infinity.